All right, so the other day in lab, what did I do? I set things on fire, right? So I turned on a Bunsen burner and I threw a bunch of salts in them, and depending on the salt that I put in, you got different colors that came out, right? And then I said to you, it would be a real pain in the butt to sit there spraying those salts into the Bunsen burner long enough for me to really measure all the lights. So it might be better for us to study elements that you could contain in a tube. And so we looked at hydrogen, helium, and neon. They were in a light bulb of sorts. And I put those light bulbs in these power supplies, and they gave off different colors, right? So the hydrogen gave off like a hot pink color, and then the helium gave off like a peach color, and then the neon was bright red. Remember that? It was very intense. And we took those lights that were coming off the bulbs, and we passed them through prisms inside of a little spectroscope, and we looked at what we call line spectra for these things. All right, so for hydrogen, what do we see? You saw maybe 4 lines, right? When you looked through the spectroscope, you saw a violet line, a blue line, a green line, and a red line. What was obviously missing in that particular spectrum? Yellow and orange. When did we see those lines? When I changed the bulb from hydrogen to helium, right? And when I put helium in, we saw more purple lines, more blue lines, more green lines. We finally saw yellow lines. We saw orange lines. We saw red lines, right? I believe you guys said you saw maybe 7 different lines. Was that right? How about that? Now, what is the key difference in terms of the atoms, hydrogen and helium? What's different about them? Let me rephrase that. Why did I start with hydrogen? It's the first element. It's the simplest element. It only has 1 proton, 1 electron, no neutrons. Right? And then we took and switched the tubes to helium. Helium is a little bit more complicated of an atom. It's got 2 protons, 2 neutrons, 2 electrons. So we've got a tripling in the number of particles that are in the atom itself. All right? So then we took that bulb out of the power supply, we took the helium out, and I replaced it with neon. And I chose neon. Neon is a noble gas. It's element number 10. That's an even more complicated atom, right? So we've got 10 protons, 10 neutrons, 10 electrons. And what did you see? Did you see something that looked more like the whole rainbow? Yeah. And so what do we conclude? The more complex the atom, the more lines you would see on a spectrum. All right? And so that's summarized right here in that little paragraph that I want you to jot down. Bohr did the same thing. Except for he took it one step further. He theorized that because more complicated atoms had more complex spectra, that must tell us something about an atom structure. And we're going to spend the whole week trying to figure out what that tells us about an atom structure. Yes, sir. You sure can. Here, you want me to zoom in a little bit more? No. Evan's desk is worse than the desk that you're in. In the corner? Huh? Corner? You like the corner? You want to be against the wall? But that's where you are. It's like 2 inches forward. Do you need glasses? Are you complaining about my handwriting?
No.
Yeah, he is, right? He said he's not blind. It's just he can't read
I
it.
thought it was spectrum. I was thinking the word spectrum.
Oh, okay. No, spectra is a plural of spectrum. No. All right, so before we really talk about how he tied light that comes off of these different elements when you give them energy, how it ties to the atomic structure, we have to really spend a little bit of time understanding some of the characteristics of light. All right? And so that's what we're going to do next. So I want you to copy this down. All right? So what I want you to do is I want you to draw this violet colored waves. There's 9 of them, and then the red waves. And I want you to write down this stuff here on the right hand side. So what I have here is in the same distance, this is labeled 1 second. I've got 9 whole waves going through there. And here in that same span of distance, in 1 second, I've got 3 waves. This here looks like a little cursive V. That's the letter nu. That says 9 per second. This says 3 per second, and here that says E equals high. Down there it says E equals low. Oh, and I forgot to add something to this picture. I forgot to add another letter. That letter looks like an upside down Y. It's the letter lambda. I'll draw it down here as well. Lambda. And I'm not going to tell you what those things are off the bat. I want you to try to see if you can come up with definitions of what lambda, nu, and E are before I even open my mouth. Where? No, it's like an upside down Y. It's the Greek letter lambda. Yes, ma'am. Say what? It doesn't say 91. It says 9 per second. 9/second. It looks like a cursive V. It's the Greek letter nu. All right, so that upside down Y right there, that's lambda. That cursive V is nu. Okay. And E is for energy. Yes? What's happening? Nu. N-U. These are Greek symbols. All right, so let's define these things. What do you think this lambda stands for? Patrick. So that's a wavelength. So lambda is wavelength. All right? And if you have to define wavelength, what would a good definition be? It's the distance from peak to peak. Or what if I measured it from trough to trough? Would it be the same distance? Yeah, it would be. Okay? Trough is the bottom of the wave. So lambda, the wavelength, is the distance from one peak of a wave to another. What's new? Look. So this has a new of 9 per second. So how many waves pass through a point in 1 second? There's a name for that. Does anyone know what that's called? Yeah. What? No. Let me give you an example of this word used in the English language. So I'm an old lady. I have a small bladder. I use the bathroom frequently. What does that mean? I go often. I pee a lot, right? Often. All right? So how often these waves pass through a point in 1 second is called what, Keanu? Frequency. All right. So nu is frequency, and it's the number of waves that pass through a point in space in 1 second. Yeah, they do. They're called frequencies on the radio, right? On the dial. Extra credit. How about endearment? You're fine with that? Encouragement? You are engaging. You're connecting. Yep. Okay, so it's obvious that the violet light has a higher frequency than the red light, right? Because there's 9 waves passing through a particular point in time, which is 1 second. Usually that's how you use the measurement, versus 3 waves. All right, in terms of energy, violet light has high energy, red light has low energy, but don't take my word for it. Let me explain it to you in terms of an analogy. Let's say, for instance, I was swimming in a purple ocean, and I was treading water and trying to stay afloat and trying to keep from drowning, versus treading in a red ocean. Where would I have a tougher time? Where would I have to spend more energy to keep from drowning? In the purple ocean. How come? Because I've got 9 waves coming at me in the span of 1 second. And they're short, choppy waves versus long, rolling waves. Okay? This has a lot more energy than that. Okay? So, let's look at these relationships. So when wavelength is low, frequency is high. Let's write that down. When wavelength is low, or vice versa, when wavelength is high, frequency is low. Right? And I'll scooch this up so you guys in the back can see this. What about in terms of energy? When wavelength is low, we already talked about that. When wavelength is low, what about energy? Energy is low. No, energy's high. If I was sitting in an algebra class and my teacher asked me to describe this relationship, like so when one parameter goes up and the other one goes down, what's the term that they use to describe that? When one thing goes up and the other one goes in the opposite direction, what do we call that relationship? Patrick, you want to give it a shot? No. You have one of two choices, direct or inverse. It's an inverse relationship. All right, you need to know that term. All right, well, what other relationship did we just see in that graphic? How about frequency? When frequency is high, what happens to energy? Really? When frequency energy is high? What happens when both variables are pointing in the same direction? What do we call that relationship? That's a direct relationship. No. So you need to know that wavelength and frequency are inverse, wavelength and energy are inverse, frequency and energy are direct relationships. All right? The other thing you need to know and have committed to memory is that purple light has shorter wavelength than red, and purple light has greater frequency than red. And you don't have to memorize all this part, because it would make more sense for you to memorize this, that purple light has more energy. If you memorize this part, just this one, you can work out those two. All right? Well, what's one way of memorizing that purple light has more energy than red? Well, again, since we're, so into wanting to connect to other parts of our lives today, right, County? All right, when you go outside in the summertime and you burn your skin, what's burning you? UV. UV stands for ultraviolet. What color is violet? Purple. The purple stuff is the stuff that hurts you. It has a lot of energy. It burns your skin. All right? What about when you go into the cafeteria and buy one of those chicken sandwiches that are like hockey pucks? Are they sitting under those red lamps? That's an infrared lamp, right? Does that infrared lamp really heat up that sandwich? I have never eaten one that's actually warm, right? It's because it doesn't have that much energy in it. So just remember that. The violet stuff is what burns you. The red lamp that the sandwiches sit under doesn't really do a job very effectively. Okay? So purple has a lot of energy, red doesn't have a whole lot. And if you know those differences in energy, you can work out the differences in frequency, the differences in wavelength. Okay? So far, so good? Yes. Fabulous. Now I'm going to show you how to do the math behind this. It's easy. But it is going to require that you memorize a couple of equations. It is going to require that you memorize a couple of constants that go into those equations. All right? So, go ahead and open your textbook to page 141. Pull out a calculator, please. And you can put the coloring pencils aside for a little while. You may. Just put the thing in the door, please. 141. All right, so let's start with this. There's an equation available to us that allows us to convert between wavelength and frequency. So if you know the wavelength of a photon of light, you can calculate its frequency, or vice versa. If you know the frequency, you can calculate its wavelength. And the equation is up here on the board. So it's C equals lambda nu. but two of those symbols that are in this equation, you already know what they are, right? What's this one? Wavelength or lambda. What's that one? Frequency or nu. How about C? What is C? That's the same C as in Einstein's equation, that E equals mc squared. Anyone know? All right, I'll let the cat out of the bag. C stands for celeritas, and that's just fancy for speed of light. All right. The lambda is wavelength. I want you to write this down in parentheses. This is a unit that you're going to use for wavelength. Most of the wavelengths that you and I are going to measure are the ones that are visible to our eye. Our eye can only detect things in the visible light spectrum. Those are on the nanometer scale. So the unit for wavelength is going to be in nm. And the frequency is that letter nu. The units for frequency are the hertz. So like it's spelled just like the car rental company, H-E-R-T-Z. You abbreviate it Hz. Or if you're sitting in a physics class, they might use 1/second instead. So we call that a reciprocal second. Or if you wanted to write it with negative exponents, s to the minus 1 power. So seconds to the minus 1 power. These three things were synonyms. Hz. Alright, well let's talk about the speed of light. The speed of light is a well-established number. It's been measured in a vacuum. And it doesn't matter if we're talking about purple light or red light or blue light, or if we're talking about gamma rays or X-rays. All these kinds of radiation in a vacuum, as they travel through the universe, travel at the exact same speed. Does anyone know what that is? Yeah. Miles an hour. Those SI units, Evan. That's pretty good. Yeah. No, I need you to know I'm an SI. It's a number that you're going to memorize, and the number I'm going to give you is a little different than what you might see in textbooks. Textbooks are going to give you this number in meters per second because those are the SI units for length and time. I would prefer for you to memorize this number in nanometers per second because it's going to help you out in the long run when you do these calculations. All right, so speed of light. It's a number you memorize. It's 3.00 times 10 to the 17th nanometers per second. All right, so make sure you write that down. Make yourself a little note that you have to memorize that. Ten to the 17th. Okay, so we're going to go ahead and do sample problem 5.2 on page 141. And so go ahead, open the book to that page. I'm going to put it here underneath the camera so you can read it along with me. But it's just easier for you to look at the page in front of you. All right. Can I scooch this up a little bit? Yeah? All right, so here's the question they're going to ask. They want us to calculate the wavelength of yellow light emitted by a sodium lamp if the frequency of the radiation is 5.09 times 10 to the 14th hertz. All right, so when you're doing these questions, I want you to start by writing down what they're giving you in this question. What are they giving you? The frequency, all right? So, this is what I write down. I write down that nu, the given is that nu is equal to 5.09 times 10 to the 14th hertz. What do they want? Look at the prompt. What are they asking here? calculate the wavelength. So what's the symbol for wavelength? Lambda. So what do they want? They want lambda. Do you have an equation with those two variables in it? Yeah. What equation do you have? So go ahead and write that equation down. I always start by writing the equation down first step. Don't jump ahead and substitute in, and forget to write down the equation first. Always write down the equation first and then show the substitution. All right. Let's take a look. Do I know what C is? Yeah, how come? Because I memorized it, right? So I'm going to go ahead and write it in for C. Do I know what lambda is? No, I don't. Do I know what nu is? Yes, I do. Right, so you just substitute in. And now in algebra I learned that if I want to get lambda by itself, what do I do to both sides of the equation? Divide both by? By what? 5.09 times 10 to the 14th. All right? Now, remember you're sitting in a chemistry classroom, right? Do I have to worry about the number that I get out of my calculator? About having it be formatted correctly? I do. All right? I'm dividing. So what do I worry about when I divide? Sig figs, right? How many sig figs are there here in this numerator? There's 3 sig figs. How many sig figs are there in the denominator? 3 sig figs. And so when I put this in the calculator and spit out an answer, which I'm going to do right now, so 3 to the 17th divided by 5.09 to the 14th, all right? And my calculator says that. What do I write down? 589, because if I look at the neighbor, does the neighbor merit me going up to 510? No? So, or 590. So 589, what is that unit? Nanometers. All right. It's really, really important that you don't just give me a number, you give me a unit as well. Did I kill you guys on the last chapter test with units? I did. I'm going to do it again. I'm going to keep doing it all year long. I need units on numbers. It's really critical. Yeah, Jeff? Yes. Well, no. So when you substitute in? No, you can leave the units out when you substitute in. Just make sure that your answer at the end, that you have the units written on them. I put them in there because it helps me figure out the units. But for instance, I would just urge you to memorize them. So memorize it. Wavelength has to be in nanometers. Frequency has to be in hertz. And energy has to be in joules. So long as you just memorize them and you just write them down at the end, you're good. Brian? Oh, I'm sorry. It should be 589. You're right. 589. Lexi, is that what you were going to ask? What were you going to ask? Oh, you have your calculator set to scientific. Okay, that's fine. If you leave it in scientific, it's fine too. All right? So now I'm going to give you a question that's not in your book. And I want you to write the question down, and I want you to work it out on paper. I'm going to turn the lights on, and I'm going to walk around, because I want to see how you're doing this. And I'm going to come and stop at each one of you individually to see who needs help and who doesn't. All right? We're going to work it the other way, too, while we're at it. We're going to call this extra practice. I can't believe you're yawning. This is the most exciting lecture ever.
Hell yeah.
It's all right. All right, so here's what I want you to do. I want you to calculate what the frequency of light would be if you have a wavelength of 462 nanometers. 462 now. Turn the lights on. Freak out. 462 now. Alright, so go ahead. Start with writing down the equation, show the substitution, and then solve for the final answer. Calculator again. Oh, you know why? This is 3 times 10 to the 17. do? You forgot to look all the way to the far end. Make sure you're missing the extra from that. Yeah, you have to run that. No, it's this times this is equal to 462 times new, right? So we do that. So now if I want to get new by its side, by what? By 462. So you divide this side by 462, and then you divide this side by 462. That's good. That's not anything. Yes. That's correct. Write the equation. What was the equation? Write it down. No, write the equation. Write it down. Now we're going to substitute L. Do you know L? Exactly. So that is Alright, who did not get checked? I'll read it right here. You're good with units. You have to hear about it. Meters is a length unit, right? Okay. So wait a minute. Wavelength is a minute. Frequency is a what? Okay. That's still not right now. Show me on your Alright. Yep, that's it. Unit's not right though. This isn't meters. Meters are a unit of length, right? That's not frequency, that's wavelength. Frequency is in hertz. So you write HZ. Alright, what did you guys get? 6.49 times 10 to the 14. Did you get that finally? Once you divide it, okay. 6.49 times 10 to the 14 hertz. Alright. I'm seeing some algebra skills that definitely need brushing up. And this is like stuff you should have learned like in the first week of Algebra 1. And these are not skills that you have like been asked to, that haven't come back up again and again in your math classes, so I'm a little taken aback, but we're going to work on that. All right, so you start by writing the equation, C equals lambda nu, all right? We know what C is. It's a number that you memorize. You substitute it in. You know what lambda is. It's in the question. It's 462. You substitute that in. Nu is what you don't know, all right? So right now, as written, I'm multiplying these two numbers, right, these two variables. To undo that, to get V by itself, I would have to divide both sides by 462. All right? And so then if you look at what you've put into the equation, I've got a 3 sig fig number divided by a 3 sig fig number, so whatever the calculator spits out, I should write to 3 sig figs. And so what again was that? 6.49 times 10 to the 14th. And what was the unit for frequency? Hertz. Not nanometers, because meters are a unit of length. That's for wavelength, not for frequency. Okay? So, part of your homework tonight is going to start on page 141. You're going to do questions 15 to 18. The first two questions, you're going to have to do these kinds of calculations. On top of that, on those two questions, they're also going to ask you, based on what you calculate, does this have more or less energy than a different color? And so you're going to have to go back to page 139. There's a little graphic here that you'll have to refer to that tells you like the different wavelengths for different colors. So, for example, red light has a wavelength of around 700 nanometers, and the frequencies are down below in this gray table. And then the violet light has a wavelength of 380 nanometers, and the frequencies are down here on this table here. All right? So for 1516, you'll have to do the math plus look at this graph, or this graphic. Okay? All right. Yes. Say what? 15 through 18. It's only 4 or 5 questions, right? Okay, let's keep going. Here's the second equation that you need to know for today. We also have an equation that allows me to calculate the energy in light. But it requires that I know the frequency. All right? And so that's the equation that you're going to use. E equals h nu. What's the E stand for? Energy. Good. What's the nu stand for? Frequency. H is something that's brand spanking new to you. H is a number, another one that you have to memorize is called Planck's constant. It is equal to 6.626 times 10 to the negative 34th, and the unit is weird. It's a joule second. That says joule dot second, joules times second. Physics likes to use a lot of derived units. This is one of them. On page 144, we're going to look at sample problem 5.3 next. So go ahead and open to page 144. Let's see what they ask. Yes? Yeah, I can. You want the formula? so sample problem 5.3, I don't know if it's necessarily on the screen, but again, you have the book in front of you, you can read it out of the book. It asks, what's the energy of a photon of microwave with a frequency of 3.20 times 10 to the 11th reciprocal seconds? Or hertz, the same unit. All right? So guess what I do? So for this particular question, again, I start by writing the equation. I look at the word problem and I ask myself, what are they giving me? What do they want? All right? So in this case, what do they give me? Did they give me the frequency? What do they want? Energy. Do I have an equation in my arsenal that has those two variables in it? Yeah, I do. What's that equation? E equals h nu. So I just write down that equation. And then what do I start to do? I start to substitute in. Do I know what E is? No, that's what they want. Do I know what H is? Yeah, it's a number that I've been asked to memorize. What is it? 626 times 10 to the negative 34th. Do I know what nu is? Yeah, I was given that in the question. It's 3.20 times 10 to the negative 11th. Let me scooch this up so you can see this a little bit better. All right? Now I grab my calculator, what do? Multiply. And before I write an answer down on my paper, I look at my inputs and I ask myself, okay, well, how many sig figs does that have? How many sig figs here? 4. How many sig figs does that have? 3. And so my answer should have how many sig figs? All right, so let's see. Let me put this in the calculator. 6.626 to the negative 34th times 3.20 to the 11th. All right, that's what my calculator spits out. What should I write down? 2.12 times 10 to the negative 22nd. Okay, again, pay close attention. Nick. Okay, as you're dozing off. Okay. Make sure that you look all the way to the end and that you write down that exponent. Yes, Kevin? Well, because you multiply the numbers. Did you not get that on your calculator? I'll come over and show you how to type it in. Did someone get something different besides mine? Or are you getting what I'm getting? Are you getting the answer I'm getting? It's 2.12 times 10 to the negative 22nd. Okay. All right, so that's what you would write. Now, what is the unit for energy? Joules. And so you would put a capital J. Abby, was that your question? Okay. What other questions do you have, Jasmine? Never mind. What other questions do you guys have? All right, we're going to do 2 more problems and then we're quitting on this. And then we'll move on to the total. Because that's the unit for Planck's constant. They're called joule seconds. Yes, sir. To the negative what? Are you sure you typed in negative 34 and 11 correctly? Go back and look at how you entered it. You probably typed in the wrong exponents for those inputs, so go back and double check them. Because Madison, the truth of the matter is that the whole thing has to be right, not just the number in front, but the exponent has to be the same too. Okay? The whole thing has to be correct for you to get full credit. All right. We're going to do a question again, not in the book. One that's intended to help me go around and see who's getting it and who's not, who needs extra help. I want you to write it down and work it out. I want you to calculate this. What's the frequency of light with an energy equal to 7.18 times 10 to the negative 21st joules. And there's a decimal there. exponent is wrong. Everyone who has this calculator is getting the wrong exponent. Put parentheses around the parentheses. I think that might fix it. Okay. Yes. Did the parentheses do the trick? No. It's how you're typing it in here. So you're going to do 7. You have it set up right, but the exponent was wrong. So it's 7.128 when you do second. You see the 2 e's in second is negative 21 divided by 6.626. That's how you write it. That's the right answer. All right. You get it? So what was the answer there? 1.08 times 10 to the 13 hertz. Okay, fabulous. I'm going to show you one last problem. This is as nasty as it's going to get, and then we are done. We'll move over to the pole. All right, so as nasty as it's going to get. I'll turn the lights off so you can read it. Last problem. Last problem. It does say extra practice. It's extra. Extra. All right. As nasty as it's gonna get. What is the energy of a photon, which is like a packet of light, with a wavelength of 520 nanometers? Okay. What? That's a lambda. Where there's no what? There's no lambda where? In the energy equation. What? What? What do you mean you don't solve it? What's that? What's that, Jasmine? So what equation do you use both equations? Okay, so I'm hearing from Jasmine and from Brian. They're telling me that you have to use this equation first. Right? And what do? You plug in a 520 in for lambda, and then you solve for nu. Right? And then you take the nu and then do what? Shove it into the other equation? All right, you can do that. That is a lot of work, isn't it? Can we like use algebra to our benefit to make it less work? Yeah, we can. All right. Let me show you something really quickly. Do these two equations have a variable in common? What? The nu, right? They both share that equation. All right? You could, right? Or another way of doing that is, what if I go ahead and take this equation and isolate nu? What would that look like? How do you get nu by itself? C over upside down y equals nu, right? All I did is I divided both sides by lambda, right, to get the nu by itself. All right. Now that I have this reorganized, couldn't I just take this and plug it in for nu there? Okay, so then E would be equal to H times C over nu. And if you didn't want to write it with parentheses, couldn't you just write HC over nu? Or, I'm sorry, over lambda? Ooh, so you can combine two equations together. Yeah, you can. So how would we answer this question? So the energy, what is it? When the wavelength is 520. Okay, well, what symbol is this 520 representing? The H, the C, or the lambda? So plug in 520 for lambda. Do I know what H is? What is it? Good deal. Do I know what C is? 3.00 times 10 to the? Oh, look at that. I can do that. I can shove it in my calculator. So now on the calculator, you want to be really careful, and you want to make sure that the calculator multiplies these two numbers together. So I would use parentheses around that numerator, right, before it does the division by 520. So look at how I type it into my calculator. So I'm going to say 6.626 to the negative 34th. I'm going to start that with a parenthesis. Hang on, 0.626. So it's going to look like this. Parenthesis 6.626 times 10 to the negative 34th times 3.00 second e to the 17th. Close the parenthesis. Divided by 520. All right? Now, look at the inputs. How many significant figures were there in this number? No, in the 6.626. There's 4. How many here? How many there? No, that only has 2 significant figures. All right, so how much of this do I write down? So what would I write? 3.8 times 10 to the negative 19th. What's the unit for energy? Joules. Okay? All right, are we good? Your homework on it starts on page 141, is to do questions 15 through 18. It's just using these equations over and over and over again. All right? Let's stop this.